Okay, let's get started. Our second keynote speaker is Ilya Sergey from National University of Singapore. And Ilya has done so many works on semantics and languages, smart contract languages. And for today, today's talk title is Multi-Modal Verification of Distributed Systems in Lean. So please join me in welcoming him.
Thank you so much, Hector, for the introduction and for the invitation. I realize that I'm competing for your attention with the session of distinguished ICFP papers, so even more delighted that you have come here. So I hope to make it worth your while. I'm going to talk about the work that I'm very excited about. This is something that has happened over the last year and a half. And as always, the main credit goes to my PhD students, Georgia Perle, Vova Gladstein, and Chuan Zhao, and also Elad Kinsbrunner, who did an internship with us. So the theme of reasoning about distributed protocols and distributed systems has been a long-running topic in my group, and this work is about consolidating many ideas and many lines of thinking in what we hope is going to be a significant advance in making verified distributed systems a reality. So the title has the word multi-modal in it, which might be unfamiliar to some of you, so let me unpack that. So in fact, what I'm going to present is a framework that allows you to reason about distributed protocols in a way that combines both automatic reasoning techniques with interactive proofs. And for all of that, we are going to use Lean as a lingua franca, as main encompassing framework. So let's start from the basics. Distributed protocols are algorithms that define how multiple parties, typically called agents or nodes, collaborate together to achieve some common goal. And this is a problem which is almost as old as computing, and many of us know the classical papers such as the times clocks and the ordering of events by Leslie Lamport, the algorithms for mutual exclusion such as Ricard-Agarwala or Suzuki-Kazami constructions, or constructions which are very prominently used in distributed systems even today, such as the two-phase commit. So I couldn't find a canonical reference, so here is the slide from Leslie Lamport's video class on TLA+, which is a fantastic teaching material, by the way. Consider checking it out. So he explains two-phase commit in terms of marriages. So the story doesn't end here, and distributed protocols, they become really interesting when you realize that their main purpose is to connect the parties across multiple physical locations. And when we have these geo-distributed systems, some nodes, some parties might go dark, might stop responding, the messages might be lost, and we can experience all kinds of failures. This is when the problem of specifying and reasoning about distributed systems becomes interesting, and this is the problem to which we owe some of the most prominent constructions, such as the view-stamped replication, Paxos consensus protocols for reaching the agreement between multi-parties, and many other things. So some of these works are more modern, some of them are by my colleagues, but this is still a very much active area to develop protocols for reaching an agreement in the presence of failures. But the story doesn't end even there, because not only parties might fail, they might intentionally misbehave to make the protocol, to make it difficult for the honest participants to achieve the agreement. And you can think of systems such as blockchain protocols, where people have like very real financial incentives to behave maliciously, so they can, for example, double spend the digital currency. This is a very popular problem, as many things in distributed computing. The name has been coined by Leslie Lamport as the Byzantine general problems, when multiple generals in the Byzantine army try to agree with each other by sending messengers, whether they attack next morning or whether they retreat, and some of these generals might be traitors. So this is the analogy that goes a long way, and this is what has been used as a main premise to build protocols for what's called Byzantine fault tolerance, with probably one of the most famous one being the PBFT by Miguel Castro and Barbara Liskov. Yeah, that Liskov of substitution principle. That's the same person. So, and there are other more popular constructions nowadays, such as hot stuff and protocols for stellar consensus and others and others and others. And actually, this is a very active area, and at least 5 or 6 papers on the BFT protocols are published at every major security conference, such as Oakland or CCS or Usenix every year. So people work on this stuff quite actively, and obviously they're very much interested in getting these protocols right. Not just their implementation, but the algorithmic design of these systems. And bugs in these protocols, they happen surprisingly frequent, and they are published in the papers, and they sort of poison the implementation. So George, who is one of the main drivers of this work, even keeps this list on GitHub for bugs in distributed protocols that keeps being updated with people submitting PRs with more stuff being discovered. So what kind of manifests the bug? So a bug is a violation of one of the desired properties. And those properties that we want to enforce fall into 2 classes. As we know, we have safety properties, meaning that bad things will not happen during the lifetime of our system as the protocol executes. And there are also liveness properties, something that we frequently specify in logics like LTL, that say that good things will eventually happen. Practitioners like to focus on safety properties more because these are the properties that can be somewhat reliably discovered with the conventional black box testing with finite counterexamples. So if the bug happens, you have a chance to run the system until it happens. If your bug means that certain events will never happen, this is much more difficult to discover unless you do a very deep intrinsic analysis of the workings of your system and try to detect something like cycles in its logic. Okay, so let's focus on how can we verify the properties of distributed protocol, safety or liveness. And indeed, this is the problem that has received quite a bit of attention in the static analysis and formal methods communities. And some solutions to specify and formally verify safety properties of formal protocols date back at least 20 years. I'm quite sure that this is not the first paper, but this is the one which is relatively well known by Maro Jaskelev and Stefan Mertz, who proved the correctness of a version of Paxos in Isabel Hope prover. And the works were coming from their own, so some of them are more prominent, some of them were focusing not just the protocols, but the systems. Some of them, such as Ivy, delivered frameworks which are supposed to be used by the protocol designers, and these works keep coming. So what, and as you can see, like some of them, okay, I even very graciously mentioned some work from my lab, but the point is that how many of you have heard of protocols such as Lido or Bifos or Aneris or Velizarius? Okay, so this is obviously a very biased audience. None of the practitioners I've spoken to ever heard of any of those. What do they have? What have they heard of? TLA+. So TLA+ is the tool which has been conceived and designed by Lamport and then developed by folks at Microsoft, and it has an amazingly effective model checker, which doesn't attempt to do any verification in a symbolic sense. It takes the model of a distributed protocol and it just runs it up to a certain depth of the execution, which turns out to be a very effective way to discover bugs in the designs. Sure, the bugs occasionally get missed. For example, one of the known cases is how the Raft consensus protocol had bug in its definition, which hasn't been caught by running the TLA+ model, but still, this tool has a relatively low entrance threshold, and it has a very nice feedback loop. So it actually makes it quite pleasant to prototype distributed protocols, and hence industry uses it. So, but this is not something that you can use to verify that your system, well, is devoid of any violations of your desired safety or liveness property. It's a tool for bug finding. So how can we bridge the gap? So to do that, and also to make a practical tool, we need to understand what makes TLA+ so successful. So what it makes successful is that, well, the formalization effort, which is well, effectively the probability that your tool has, that your system has no bugs, it kind of, with TLA+, it's like relatively low, but the formalization effort is also low, and if you go with formal verification, you get to this angle. But people in industry, they're really not interested in the probability of having no bugs. They are interested in a very ephemeral notion of the percentage of bugs that you have found. And this is where, somewhat informally, TLA plus scores really, really high. Because if with very small formalization effort, you already manage to eviscerate 99.9% of bugs, and well, who cares that something might be lingering? It might still be critical, so you still care about that. But it's typically good enough for most of the practical purposes. So how can we get there? And how can we avoid this really, really steep curve of the formalization effort that is required out of the foundational tools to get to the same percentage of bugs? Because as we all know, if you try to write your system in your favorite proof assistant, even if you're really, really good at quick prototyping, you will probably spend quite a while until you get your first QED for the interesting property. So you will spend a lot of time proving invariance and auxiliary lemmas. So TLA plus is so successful because it has this feedback loop between the engineer and the tool, where the engineer gives the definition of the protocol and the properties with no tools whatsoever, because remember, it's just for testing, and TLA plus gives back the checkmark saying, okay, up to certain depth, I found no bugs, or it gives you counterexamples. And those counterexamples, they are very graphical, so they are as good as you can get in terms of debugging. How can we get there? And how can we also make it so from this model, we can also gradually go to verifying distributed protocols? And well, this is where we started. So we actually really wanted to get into this gray area where TLA plus doesn't do so well, which has to do with Byzantine failures. So what makes Byzantine failures, the adversaries, difficult to model is that you need to be as smart as the adversary. You really need to be able to predict every move of the adversarial player to model it precisely. Whereas if you think in terms of symbolic reasoning, it's actually much easier. You just say what the adversary cannot do for sure. For example, it cannot reverse hash functions, or it cannot forge signatures. And then anything else it can do, and this is something that you can reason symbolically. Well, so there is a small family of tools based on first-order logic, most prominently Ivy and its version MyPyWay, that actually get in this gray area, and they get somewhat better experience in terms of this feedback loop, because these are the tools that are based on decidable fragments of first-order logic, meaning that most of the proofs can be constructed automatically with the help of tools such as SMT solvers. The price to pay is that certain properties we just cannot express easily, because these tools, they work in a somewhat limited logic compared to tools such as ROC, Agda, or Lean, but they get an automation. So we really want to get somewhere here. We can get all the good things, but we can also state properties that are undecidable by the nature, and if there is a property for which we want to write an interactive proof because SMT is not powerful enough, we should have this mode. So this is a relatively narrow space, but this is what made this problem very interesting for us as researchers, and with the hope that we could also deliver a useful tool. So we want to be here. So let's try to analyze what the world has now and how can we contribute. So TLA plus is amazingly expressive, so you can write pretty much arbitrary properties and get fast feedback. If you want to prove properties, whether it's complex properties and higher order logic, or something that requires first order logic and proof automation using SMT, in principle you can do that. So not many people know, but TLA comes with the proof system, which few people use, and it even comes with some support with SMT solvers. It's just not something that it's optimized for, and the experience is somewhat subpar. So many people still use TLA plus as a glorified testing tool. However, if we look at the research that typically gets published at conferences like UPSLA, POPO, PODI, or even SOSP, this is where people really focus on interesting properties that require full-blown higher-order logic. And sadly, this is where you have close to no automation, and you have no fast feedback, because these are all the efforts that carried out by big labs, usually in the course of multiple person years, well, culminating with the paper, but no one in industry giving a damn about it. So something which does slightly better are the industrial efforts such as Iron Fleet, which pursues the same goal, but adopts a tool based on the automated prover, which was Daphne. So at least some automation has been done there, and this was actually a pretty good experiment. Ivy in MyPyWay suggests a different trade-off when you sacrifice the expressivity of the property, and you also cannot do much about the interactive proofs, although there are some attempts to extend them, but you get the fast feedback because your SMT solver either gives you the desired ansat, meaning that your specification holds, or it gives you a counterexample, and you get the automation thanks to that. Okay, how can we get all these things together? And this is what was the goal of this experiment, which resulted in a tool called Whale, which I'm going to present. So Veil actually achieves all these 4 properties, and it's still very much a work in progress in the sense that we are trying to make the user experience even better. But let me just tell you that the arbitrary properties is something that you can specify in Veil, because Veil is just a library or a domain-specific language on top of the calculus of construction as implemented by the Lean proof assistant. Furthermore, it's a shallowly embedded library, meaning that the programming language in which you define your models in Veil is very much the language of Lean itself, with some extensions for the quality of life if you want to have easier time discharging your proof applications. How do we achieve fast feedback? Well, we go full in with symbolic model checking, where we generate our queries, well, basically our verification conditions are the queries that are dispatched with the help of an SMT solver. So they are proven or disproven. And in the more modern version of Veil, which I'm not going to show, we can even run the concrete state model checking the same way as TLA Plus does. But the nice thing is that by means of being just a library on top of Lean Proof Assistant, we can also have interactive proofs for the properties that are not easily dischargeable with an SMT solver. And as mentioned, by using an array of tools that interface between the higher order logic of Lean and the first order logic that SMT solvers take in the form of SMT lib queries, we can also prove many obligations as just push the button without writing any proof script in Veil using SMT solvers. Okay, so that was the premise of what we wanted to get and what ostensibly we have achieved. And I'm going to spend the rest of my talk trying to convince you that we are either there or at least on the right path, and see if you have some feedback which we would like to incorporate. So to show you the tool in action, let's go with the hello world of verified distributed protocols. Really the simplest application that usually comes to mind when someone wants to specify a distributed protocol, which is a leader election in a ring topology. So the idea is very simple. We have the finite known number of nodes with identities, and the nodes themselves, they only know the identities of them, like of their own, but not of the other participants. But the identities, let's say natural numbers, they are totally ordered. Not necessarily contiguously, there might be gaps and whatnot. So the goal is for this bunch of nodes to select someone that they perceive as a leader, and for the node that is selected as a leader to know that it is a leader. So how that is achieved? The protocol is actually very simple. So each node sends its own, and each node also knows the topology in the sense that it knows who is its next neighbor. So you can think of it ordered clockwise or counterclockwise. This is actually not that important. So each node only knows its next neighbor. So each node sends the message with its own identity to its next neighbor. For example, the node with identity 1 sends its identifier to 5. And so do all other nodes. And each node, upon receiving the message, if it has received with the node with the larger identifier, it then passes it through and sends it to its next neighbor. Otherwise, it just consumes this message and mutes it. So for example, the message from 1 to 5 doesn't go any further because 1 is smaller than 5. But the message from 3 to 1 goes further, so by 1 relaying it to 5 because 3 is larger than 1. And as you can imagine, what's going to happen is that after the protocol kind of comes to the stable state, there's going to be only one message that, well, logically made the full round. And this is the message from the node with the larger identifier to itself. In this case, the message from 5 to 5. So the node with this identifier, upon receiving the message from itself, knows that it has made the full round, which means that it is indeed the largest identifier in the ring, so it can proclaim itself to be the leader and start acting as such. And this protocol doesn't assume any sort of faults. Again, it's a hello world example, so we don't assume that the nodes, for example, lie about their identity. So, and when someone starts acting like a leader, all the nodes will supposedly take that this is the case. However, this protocol is subject to one non-trivial property. How do we know that there is exactly one leader? Well, humans are really good at mentally executing state transition systems. So running it on a bunch of finite examples in your head, you will see that it's highly unlikely that there will be two leaders because effectively only the largest message will make the full round. But this is non-trivial reasoning. And the fact that there will be at most one leader at the protocol is a safety property that we want to hold over this system. So how can we specify and how can we verify that? Okay, so effectively, once the leader is elected, we want to make sure that there is at most one leader, or at any point of time there is at most one leader, because if like no leader is elected, then well, there is no leader. Okay, and this is something that I'm going to use as a running example to show how well works from the perspective of its user. So now I'm switching to, well, VS Code, well, in this case Cursor, but I'm not going to use any fancy AI to assist myself, and I'm going to show what the encoding of this protocol and what the verification looks like in Lean. So what you're looking at is, in fact, Lean, except, well, there are many keywords that are not really Lean keywords, well, because vanilla Lean looks more or less like your favorite programming language. So this is what vanilla Lean looks like, with some theorem, which in this case is proven using SS-reflex, so you don't have to know that, but this is a functional language. What I'm going to show you, it doesn't look like a functional language because, and this is the one main reason why we have decided to go with Lean, of an amazing power of Lean's metaprogramming. So effectively, through clever manipulation with the syntax and staging your passes, you can make Lean, you can disguise Lean to look like pretty much any language of your liking. So here, the story starts by us importing Val as a library and opening the module in which we are going to define a distributed protocol or just a state transition system in Val. So for that, we actually need surprisingly few components. And since we are interested in symbolic reasoning rather than concrete runnable implementation, which is something that I will leave aside in this talk, we actually don't need to provide that many details. For example, we don't need to say what is the exact type of the nodes. That might be integers, they might be strings, they might be reals, but importantly that this is some abstract type whose elements are totally ordered. So, and people who do proofs using SMT solvers, they can recognize of that as just us adding a theory of total orders into our context. So the tool could probably make use of that when it tries to construct the proof. Since this is a part of ICFP Splash, so talking to the ICFP crowd, how would you implement this theory? Well, the good news that this is just a type class in Lean. So you can think of it that this whole verification is happening in the presence of an instance of this type class, but the instance is not required unless you will try to run it. You can just assume that you are implementing something that comes with this dictionary of facts and the dictionary of relations. So in addition, we want to describe that our nodes, they are ordered in the ring topology, for which, for historical reasons, we have this between type class. And I'm not going to go too deep into explaining this relation and for axioms for it, but you should believe me that basically that means that any two elements are in the ring topology and they are reachable from one another. Okay, so armed with these two theories on our nodes, we can now define our state of the protocol and the semantics of our protocol in the form of what can happen. The state is also quite simple. So we could define it as a data structures, but again, since we are going to use SMT a lot, a better choice is to define the components of our state as relations. You can read it as functions from node to bool, or in this case, node to prop. Like difference between bool and prop in this case is actually not that significant because we are reasoning about types with decidable equalities, and everything here is going to be decidable. In any event, so leader is something that says who is the leader. And this is something that assigns true or false to a node. And pending is the set of messages in flight. So instead of saying that this is a set, we just say that between the node, the source node and the target node, that there is a message. So this is a from and this is a to. And this is something that we model as a relation. So this is the state of our protocol. And in fact, again, this is not something that you have in the vanilla Lean. This is just a macro that generates Lean structure that has these two fields as relation and a constructor to make its instance. So what we are going to define next is an operational semantics of this protocol that says how it starts and how it evolves. So how it starts is, well, by saying that no one is a leader. So this is the a certain syntactic convention that we took from the tool called Ivy, because lots of our examples came from it, and we thought it would make things easy to port, and people are sort of okay. So syntactic convention is when we write an undefined capitalized name. That means that's a variable which is universally quantified before this statement. So this sort of saying, like, for any n within our node type, make it not a leader. So make this the value of this relation false. And similarly, there are no messages in flight between any two nodes. So hopefully that is reasonable. This is not the only way you can define it, but this is the one encoding with which SMT solvers work quite well, and which is a fact that is known in the CAF community. So now going to the operational semantics of our protocol, we can say when it's okay for node n to send a message to the next node. So it turns out that it's okay only to send when the next is the immediate next node in the ring topology. So this is some kind of a mouthful, but in fact it means that there are no other nodes between n and next. And this is something that we also able to abbreviate later, because this is actually a very useful definition into what we call a ghost relation between the node and the next node. So meaning that, well, next is really a next. And then this is how we send the message. We just say that, well, now there is a message between n and next. So far, so good. Those of you who have seen some TLA+, this is actually not very different. So in TLA+, everything is a record or an array, and you basically set the entries of certain arrays to particular values. So this is about sending. So when a node receives a message with the ID of the sender ID in it, certain things might happen. So we know that in this case, this message should be present, the message from some ID to the node n. And here, just for the fun of it, we might either decide to keep this message, and this is a funny feature that allows you to model things such as non-deterministic duplication of messages. This just basically says, make this either true or false non-deterministically. The protocol will work either way. We can make it more strict, but this is just to showcase that as a specification language, well, also allows for non-determinism. Something that, well, it's kind of has a finicky semantics if you try to think in terms of pure functional programming. The interesting part happens here. So the node n, if it happens to be the ID of the sender, then we know that we are the leader. So this leadership relation becomes true for the node n. Alternatively, if the node itself is smaller or equal, well, in this case, strictly smaller than the ID, we relay this message to whoever is our next. Other than that, the message is either consumed in case this has been set to false, or just we leave things as they are, so the message can be received once again. So the protocol is idempotent in this sense. But again, this is the property that we can verify and something that we don't have to believe. So this effectively is how you write your protocol specifications in Val. And the nice thing, this is just one way. And what you're looking here is the mix of vanilla Lean and our macro embedding of the verification language into Lean. For example, if then else is not a syntax that we had to encode as AST and mask. So this is actually Lean's vanilla if then else. And this assignment is something that we had to model, but the sequencing of this and this is actually something that, and since this is ICFP, I can say it openly, this is a monadic bind that changes the underlying state, symbolic or concrete accordingly, and this is where like all the magic of Lean comes in how it generates the theorems that we are about to prove. Okay, but so far, let's just think that, let's just agree that we have an informal understanding of this semantics, and actually these transitions, they have multiple semantics, and we will see why that matters. And focus on the properties that we want to prove. So here's the property is the safety. So this is exactly what we had in the slide, saying that for any L1 and L2, if they are both leaders, then L1 is the same that L2. Quite a few things are commented because they are not necessarily to validate those properties, but since we want to have this quick feedback loop between the protocol designer and the verification tool, let's try to make sure that our protocol is actually not flawed. So this property does indeed hold. And it turns out that for that, we can go for a much cheaper solution than to verify that this property is not violated at any moment of time. Instead, we can say, well, this property is not violated after taking any 5 actions in this protocol, assuming that there are only 3 nodes in our protocol. So like we are making artificially a very small set of nodes, and we perform what's called symbolic model checking. So the reason why this is weaker than the verification that you typically want to have is that, well, we didn't model it for any arbitrary number of nodes, and we didn't model it for any arbitrary number of transitions. We had to finitize both. What makes it symbolic is that, in fact, we did not have to say which transitions we are going to take. So the tool has tried all of them. Where's the magic comes from? Oh, and at the end, we need to make sure that the property holds. And if you are puzzled, why do I have a negation here? Well, that's just because of De Morgan's law, right? And how the SMT solvers work. So the SMT solvers, they are very good to prove existential quantifiers, that there exists x such that phi of x. But if we want to prove that for all x, phi holds, we need to negate 5 and hope that SMT solvers will find no witnesses to that. So there is no x for which not phi of x holds. So that's why we negate the leader, and we really hope that SMT solver says that this is unsatisfiable situation. So this is unsatisfiable formula. But what exactly is the theorem that we are trying to prove? And this is kind of the big reveal. What you are going to see is just a lean theorem that the tool generates from you from the definition of the system that we have done before and this property. And the theorem effectively is like this. So it just says that, well, let's try to find intermediate states from 0 to 5 such that we can transition between each pair of them. And at the state of 5, this negated property should hold. So what we actually want to show that this theorem is not true. This is actually, this is how we're proving it. And the nice thing is that this is kind of property for which SMT solvers are really good for proving that it is either violated, so like it's not for all and there are some counterexamples, or it holds universally. For that, we have a tactic, which is actually just sending this statement of this theorem to an SMT solver from Lean, and the whole magic is thanks not to us, but thanks to an external lab, actually like the lab at Stanford, that knows how to do the translation between higher order logic of Lean and first order logic of SMT leap through techniques such as monomorphization and whatnot. So this is what SMT does, and in this case, it succeeds. So the reason why we have this squiggly line and says declaration uses sorry, which is Lean's for admit, is because we actually trusted the SMT solver. So when the SMT solver said this statement is false, we said, OK, we believe you, which is what many people are pretty much OK with, like everyone who uses automated tools. People in the interactive theorem programming community usually find this very dodgy. And, well, I have something to say about that, but, well, hold with me. So obviously, I mean, you don't have to believe that what I have shown you is legit, because maybe I have just scripted all this underneath. So let's, I don't know, let's just mess up with this protocol. Let's say, if, well, something that is definitely true holds, make yourself a leader. And you see what I've done. So now effectively anyone is a leader, because this condition is true. Well, luckily, we can go here and see that it's no longer true. And it even gives us a counterexample, which is, frankly, could be better. And in some more characteristic cases, we do pretty fine of these counterexamples. But, well, this is a research tool. So if someone actually needs badly, we will do that. So, or maybe we have already done that. So it's just my students need to update me on that. But this is a version as of. We have it on the branch. Yes. OK. So if you use a newer version, you will have it. Good. OK. So at least you see that I'm not bullshitting here. So OK, let me do something else. So OK, I just changed it to true. Let me change it to this. Will the property hold now? Yes. OK, it's nice to be in the right crowd. So there is no awkward silence, so people know how to deal with vacuously true propositions, because that's how the implication works. No one is ever a leader here, because last time I checked, it's very difficult to make one equal false if your theory is consistent. And indeed, it does work. how could we find it at the level of design? Because obviously this is made up, but what if I just made a protocol which at some point runs into some false conditions and certain execution branches never happen? Well, that's more like a liveness property, but in fact, if we think about the finite executions, then maybe we can make a hunch about it and cast it as a reachability property. So how about, so since we know that if we have 3 nodes, and there is a scenario in which one message makes the full round, which is only three transitions, and it will become a leader, and some node will become a leader, right? So it's not necessarily every scenario, but there is a scenario with 3 nodes where after 3 transitions from the start, there will be a leader. Okay, so how about we try to get this angelic scenario and make sure that it's possible? So for that, we actually have another thing, and this example, we'll say, okay, let's start from 3 nodes, and after we do one send and then receive, there should be a situation when there is a leader. And it says, nope, it's actually unsat. What does it mean for us? That means that the situation when we have a leader in the system of just 3 nodes, after one send and 3 receive, is unachievable. Why? Well, precisely because I make it so. So, and this is where we are. So, and now I'm going to change it back to the protocol and make sure that both my finite depth safety property and also my reachability property holds. And actually here, even in the version that I'm showcasing here, we do make problem model minimization. So what you're seeing here is actually a concrete example of the execution with all these 3 states in between. I mean, you need to have a little bit of training to read it, and luckily in Lean there are lots of nice things to visualize, so the sky is the limit, but you can see that we actually have a concrete example of how that is going to happen. You have the exact trace. You can rig the SMT solver to give the concrete traces of execution, which, again, something quite well known in the community. Just the nice thing that now we can do it all, not from a bespoke tool, which wraps around SMT solver, but from a proof assistant. So far, so good? Well, okay, I'm not going to stop here. So I'm actually here for the full-blown verification of this protocol. So to make things slightly faster, let me comment these 2 properties so we wouldn't have to recheck them every time we check something, we change something up above. So I'm going to go and I'm going to check that this invariant holds. So meaning that if I start from any state which already satisfies this property, and I may take one of these transitions, this property still holds. So you can think of it as a proof by induction. So we need to make sure that this invariant holds in the initial state, and it's closed under every transition. And if this is the case, then this is what mathematical induction teaches us. This property would hold at every reachable state of the system, because this is how you get to every reachable state, starting from the initial one and taking each transition. So far, so good. Well, this is not the case. Because even though this property is true, it's not inductive. So it's too weak as an induction hypothesis. So if we just assume that we have a state in which this property holds, and we take an arbitrary transition from this state, this property might no longer hold. And this is called spurious counterexample to induction. And this is something that you will have to deal in your favorite proof assistant if you try to prove something by induction, but your induction hypothesis is too weak. And at this point, we usually use all our proficiency to start strengthening our induction, or in this case, starting to strengthen our inductive invariant of the system. The nice thing is that thanks to the SMT in the loop, and again, this is something that the tools like Ivy are particularly good at doing, we can have counterexamples that give us some idea why our induction hypothesis has been violated. And if you think about, can I make a invariant synthesizer with this thing rather than having a human in the loop? Yes, this is very much what is happening. So every OSDI and or SSOSP conference in the last few years had a paper about making a synthesizer over by generalizing the counterexamples. Okay, so I'm not going to talk about invariant synthesis since I already know what the invariants here are. I'm just going to use this really cool feature of Lean support in VS Code where you can pin this line, and I'm going to change the text above it, but the effect is still going to be displayed as of me having the cursor on this line. So I'm going to go and start strengthening my invariant by adding more conjuncts to it. So I've added one more conjunct. It didn't help much because because these two conjuncts are still not closed. Their conjunction is still not closed under this transition. So I'm going to add one more. This is already better, but we still have some violation. And finally, with this one, we have everything. So what does it mean? That means that we found the strong enough induction hypothesis that not only it's closed under all these transitions, it also implies these safety properties. So the conjunction of all these properties holds both in the initial state and both is closed after every transition. And I didn't have to write a single line of proof for that. Well, I could have. Because again, this is the whole point. So this is very much the experience that tools like Ivy give you, but the problem is that SMT solvers are known to be quite brittle. So if, God forbid, you go outside of the decidable fragments, which are like relatively finicky, of the first order logic, or you have a part of the property that you want to prove interactively, well then, well, tough luck. So let me show you what kind of experience you want to have. So imagine that I want to have some extra insight of why my invariant is not passing. Remember, everything that we prove here is just a lean theorem. And SMT is just one of the, well, means of automation. It's just one of the hammers. So one thing that we can do is to ask the tool to give us only those statements that it failed to prove using SMT, for which we have this macro, after which it generates this theorem. And this is exactly the verification condition that it has tried to prove using SMT and failed. But what you're looking at is just a theorem in lean. And if you want to get extra insight, or you don't believe that SMT, because SMT might have timed out and you don't believe its result, you can just like start writing your regular lean proof script. And if you wish to discharge this verification condition interactively, by all means you can. Even more so, if at some point you manage to simplify it down to something that looks like SMT should be able to like make a quick job out of it, you can do so. Because again, this is just about using different means of producing your proofs together. I'm not going to be able to complete this proof because obviously that's not going to hold. My hypothesis is too weak, so I'm just going to roll back. But the last thing that I want to show in this demo is that even when we have everything verified and we get all the green marks as we want them, why it doesn't show? I minimize this thing. Thank you. Yeah, OK. So it's difficult to think and narrate at the same time. OK, so even though we have all the green marks, we have this pesky, squiggly yellow thingy saying, trust in SMT solvers for 12 theorems. Wow, this is unthinkable. I mean, that shouldn't be the case. OK, what am I doing? OK, CAF would actually have no problem with that. So they would cheer. So the nice thing is that we can actually have the proof reconstruction turned on, which is not something that works 100% of the time, but it works a relatively high percentage of the time. And this is, again, not thanks to us. This is thanks to a lean SMT. And now we can go ahead and we can start proving things exactly the same way. So this is just a different syntax. Here it looks more like a proof script, but here it uses more fine-grained tactics such as solve close, which is what packaged all together in this check invariance macro. So the nice thing, and we can even do check invariance, I believe. So that one will not work, no?
You have to put the option before check invariance or comment the other.
This one.
No, comment the first check.
OK, thank you. OK, so why is it blue now? There's no trust. OK, so you don't trust the SMT solver now. Why? Well, because you actually have a proof term constructed by it. If for whatever weird reason, I don't know, you like looking at proof terms in lean, I'm not a fan, but who knows? It's a big audience. Well, here it is. So this is what you're getting out of lean SMT. And well, now it's fully certified. OK, that wraps up the demo. Any specific concerns about what I have shown before I proceed to the, I have 1 hour, right, for this. So I still have like 10 minutes to talk. Yes?
In your liveliness thing, it seems to me that you're saying that there is at least 3 nodes, because you're saying that, oh, there's N1 and 2 and 3 that are not really equal
Yes.
together. But if all you know is that you have at least 3 nodes, then it's not really true that after 3 or 5 or whatever steps you can have a lead there. So how does it work here?
Well, because you're saying there might be an execution in which I don't end up with a leader after something.
You can have 20 nodes, it's still true that we have 3 that are not equal to each other, and then you can have a 20 node ring.
Not sure I understand the concern. So
Okay, so here, right, is that line not
yes, this one. Yeah, what about this?
yeah, so you're asserting that there are at least 3 nodes.
No, I said it exactly 3 nodes. Oh, at least 3. Okay, yes. Okay, sure. But that actually doesn't make a difference. So the more nodes means that I give myself more freedom. So it actually models the protocol with, yes, at least 3 nodes.
Yeah, but then if you have like 20 nodes, then you need a long time.
Yes, but that asserts that there exists a scenario in all systems which have at least 3 nodes. There is at least one scenario, which probably will involve exactly 3 nodes, where this is true. So this is the.
I see, but why is that interesting? That's not really what we care about, right? We want
Yes.
to know that in any system, like let's say,
Yes.
you
Yeah.
have n nodes, then after
Yes. So SMT solver just finds us. Example. I mean, this one, as you can see from the model, has exactly 3 nodes.
You can comment out line 101 will still work.
That's a good question. Let me try it. And this is a dangerous territory when you start fiddling. Oh yeah, it actually does work. So look at that.
So you're not really proving that in general this protocol will.
No, this is symbolic testing, if you wish. So you can think of it as me asking, is there a possibility that in some way this protocol reaches the state where there is a leader after performing these actions? And I leave many things unspecified, so this is actually up to the SMT solver to find the instances for those. Great question. Nice to have the actual implementers of the tool in the audience, so I can give more interesting demo. Okay, moving on. Okay, so obviously I have very optimistically thought that I would go faster. So just to summarize what I have shown, and I'm going to skip through the major part because that goes about the meta theory of whale, which I'm delighted to discuss, and it talks about the extra monads and whatnot, and how exactly all these things is compiled underneath using some interesting semantic shenanigans. But from the user's perspective, this is effectively what we care about. So when you define a protocol state in whale, you consists of uninterpreted types and relations. You can actually include interpreted types as well. The point is that it will make your life more difficult if you want to use an SMT solver. But again, you can always have a fallback mode with an interactive proofs. So actions update this parts of the state which are mostly relations, and the invariants are verified to hold under all actions, either via SMT or interactively. And you can test reachability or safety symbolically using SMT. Okay, so what I was planning to talk about is the details of the implementation, which has to do with how we generate verification conditions. So, okay, in the spirit of bad practice of giving presentations, I'm going to skip through most of that and effectively only say that there are multiple semantics that you might care about. So how should we interpret those actions? So we can interpret them as, so I have 40 minutes or 1 hour? 1 hour, okay, yes. So we can interpret them as imperative programs for which we have weakest precondition calculus, and then the semantic of our programs in Whale is effectively the weakest precondition predicate transformer. So it starts from the post condition, you run it backwards through the program, and you get the predicate, which is the weakest precondition. So this is what should hold in order for your post condition to be true. How would you plug that into the invariant verification? Well, this is how. So effectively, you know that if you want to have the invariant hold after the initial transition, the weakest precondition should be true. And if you want the invariant to be inductive, you know that if you assume that invariant, that should imply the weakest precondition of any action with regard to the very same invariant. So again, this is not something particularly difficult. And the last one saying that your invariants collectively imply what you want to have as a safety property. The point is that if you want to do this thing that, well, someone in the audience was wondering about, which is this symbolic reachability checking, this semantic is actually not really great. So what is great is another semantics, which is this one, which is much more familiar to people who think in terms of TLA plus, or big step semantics if you want, saying that my transitions are relations between the initial state the result and the final state. And you may forget about the result. Just think about this initial and the final state. So we have these two semantics, and they are different. And turns out that both of them are expressible. The problem is that one of them is really well behaved with regard to SMT, and another one is really badly behaved with regard to SMT. So actually, the way we want to express the semantics is through another one. And after digging a little bit through the literature and probably rediscovering a bunch of wheels, we have figured out that this is how you should express it. So saying that this big step relational semantics can be expressed through the weakest precondition semantics where your postcondition is in fact this. There's the postconditions that excludes the result and the state that you want to get and negates that. So again, says that the result and state that you want to get are not unreachable from your initial state. Yes, so I see people shaking their head, and that was exactly the reaction that we had internally in the lab when we came up with that. So obviously, you don't have to believe that. Well, the nice thing that we can actually prove the equivalence between these two semantics, and this is a nice thing of having things embedded into foundational proof assistant, is that your verifier can itself be verified. So we can switch between these two semantics at will, depending on what kind of verification we want to do for reachability or for safety property preservation, and we know that they are equivalent. With a small caveat that that only holds that if your action doesn't have crashes. So there is no assert false in the middle of it. So having exceptions in the semantics makes it even more interesting, because what to do with a transition that always crashes? Because if it just crashes, it means that it's not never taken, so it's a good thing. We can just exclude it. But on the other hand, this is a transition that blocks you from possibly reaching some states that you want. And well, after scratching our head even more, we realized that this is actually all part of even a larger picture, where this different treatment of exceptions can be expressed quite uniformly, but this is not the part of this talk, and this is something that we'll be happy to discuss offline. We have an upcoming conditionally accepted pop-up paper about this exactly. Okay, so to summarize, well, this veil is embedded in Lean, and we have the verification condition generators implemented in multiple possible ways, depending on our verification goal, and the consistency of those VC generators between each other is still verified as a theorem in Lean. So finally, the last 5 minutes, I'm just going to very briefly mention case studies. So we took many case studies from Ivy. This is actually where I'm going to bring some bad news. The tool is really slow comparing to unverified tools just based on SMT. So the red thing is Ivy runtime. So Ivy is the main competitor tool, which doesn't have interactive proof mode, and it's not foundational. It's really thin wrapper written in Python over SMT solver, and it's like faster from like an order of magnitude to like, I don't know, like half, and only in a couple of relatively small case studies, somehow we are faster than that. The interesting part is that the reason why Ivy is so much faster is that because we lose a lot of time doing the translation from higher order logic to first order logic. And in many cases, the queries we generate are actually not that bad. So this is something that might be interesting to the community, is that if we want to have a good SMT support from interactive theorem provers, well, there is certainly more work to be done about how to perform monomorphization and other translations. So the interesting part about these case studies are a few efforts that we have translated from different papers, which use the hybrid combinations of the tools. For example, Juliana Loza and Mike Dodds, I don't know if some colleagues from Galo are here, verified a protocol in a combination of two, of Ivy and Isabelle Hall, by proving some theorems in Ivy and some in Isabelle Hall. And well, turns out that, yeah, that was all correct, except we redid it all in Lean, and now we know that it was all correct, even though they had to do this translation. Some other paper actually was not so lucky. So there is an SOSP paper which had a formalization in Ivy and Rock. Really should have changed the slide. That was before the tool was renamed, sorry. So, and there, it turns out that the part of formalization has been done, okay, so, and the part was done in Ivy and part was done in Rock. So this is this paper. And what we found out is the invariant has been verified essentially in two steps. So some part of it, one conjunct, has been verified to be inductive in Ivy, so which is very good in dispatching goals in first order logic. The other part of the invariant that they wanted to prove was not in the first order logic, so they couldn't immediately prove it in Ivy, but turns out that this part was implied by the red part. So they ported the red part from Ivy into Rock, and verify this implication in ROC. And sure enough, there were typos when doing this porting. And something that we have discovered because, well, that's the benefit of having one and the same system. Okay, I don't have that much time to grill you over this discrepancy here, but if you notice that here, PSAC is a successor of SAC, and this stands in one of the assumptions of this theorem. And here we say that if it holds over the, so here it holds over the successor, but here if it holds over successor, it also holds over P. So this is what they wanted to have, and this is what they included as, this is actually what holds true, so it holds over the successor, but this was included as an axiom. So it effectively holds over predecessor. And that's highly domain specific, and this is a small typo, but that's something that changed the whole course of the proof of the property that they wanted to have. Luckily, the property still held true. So, but that's the benefit of having the same thing in the unified system. Okay, so with that, I'm approaching the conclusion. We have lots of things to do. We actually are very close to having a full-blown T-style model checker, where you not only can symbolically verify, but you can actually run things and do all these TLA plus puzzles. So we are looking at the better generation of SMT queries to speed up the symbolic part. And in the long term, we're also thinking about doing the Iron Fleet style proofs between the Veo models and more realistic implementation in Lean that you can deploy and run. Lean is a pretty decent programming language. Lean itself is implemented in Lean. And we also are developing a library for composing and implementing Leibniz proofs, which is similar to what we have done before in ROC, but this part is yet not supported in Veo. And just to take away, what I've shown you is a Lean library for multi-modal, i.e. automated interactive verification of distributed protocol in Lean. It's a shallow embedding. It takes full advantage of Lean as a programming language. It's foundational, because verification condition generators are verified to be consistent with each other, and it has reasonable performance when it comes to automation, but also gives the seamless integration of interactive proofs. That's all I have. Thank you so much.
Questions?
Hey, Ilya. You tempted me away from the distinguished papers session, and I'm so glad you did, because it was a great talk. Okay, so I have a question. You mentioned that, you know, a thing that TLA plus doesn't do well is actual verification, right, as opposed to just model checking. Another thing that TLA doesn't do well is it's not an actual implementation that you can deploy, right? And there's not any connection between your TLA model and the thing that you deploy, right? So maybe you sort of answered this question already in your future work slide when you said you wanted refinement proofs, right? But I guess that was going to be my question, right? Like a thing that Veil does not do today is actually connect proofs to runnable code, I think, right?
That is correct, if I can start the response. Thank you so much, Lindsay. Yeah, that is correct. Although Veo gives you exactly what is the high-level verification layer of Iron Fleet did, which is defining the state transition systems and proving the safety and hopefully the liveness properties. The next thing that we are planning to do, and I think we have all the tools in place with the stuff that I didn't present, is to make those models to be the ghost code for something that you actually run and prove the refinement through the manipulation of the ghost code and ghost state. That's right. That's right. Sky is the limit. If you want to do deductive synthesis of something runnable from this, I would be very excited to explore that and collaborate. Well, this is possible. Yeah, absolutely.
We have 2 minutes. So.
Yeah.
Hi. So a lot of times when you're designing a distributed system, you want to kind of like modularize it, so have some sort of underlying network layer that gives you guarantees, like maybe causal delivery or something. So in this language, have you looked at like how to modularize definitions like that?
Yeah. Great question. The short answer, yes, we have, and we don't have it yet, but we have a very good idea how to do that. More technically, this is something that you would do through sort of assume guarantee relations. Ivy has done that, and in Lean you can do that through the mechanism of type classes. Well, stay tuned, that's all I can say. But
Okay,
we very much recognize this, the need for modularity. Philippa, I think that should be the last one, right?
Yeah.
Hi, Ilya. Great talk.
Thank you.
So in Rock, we know that, for example, you can do SMT-lib inside Rock, and so you've got a connection out to the SMT solvers through that mode. I don't know enough about what's going on with Lean. Can you say a bit? I mean, do they do a similar sort of thing?
Yeah. Okay. So the question is about how exactly bridge to SMT is supported with for Lean. Actually, I have to admit I don't know how SMT Coq does nowadays. It's been a while since I tried to use it. It was very brittle. In Lean, the tool that does
so at the moment, I think it's only on the Booleans and bit vectors.
Okay.
So
I see.
And
Okay.
that's all they needed.
Yeah. So I'm not an expert here. So Clark Barr's group has a fantastic paper at this CAF this year on Lean SMT, the tool. And what happens is that for CVC5, they sort of make SMT solver to reproduce a trace that they then render consistently into the proof term of Lean, which you can interpret in Lean, and after that you can check that this is indeed a proof of the theorem you want. So it's you can think of it as a translation validation done for the SMT solver.
Thank you. And also sort of a bit related to this, which is in our sort of world, is this, I haven't seen anything like this in Lean before. Have you sort of basically shown this two-world thing, or are there lots of other examples?
I think we're the only game in town. So
I think so. No, but I think so too. But
at least according to Lean FRO, Stanford, Amazon, and Google, they haven't seen anything like this. So we showed it to all of them.
Well, it shows it. It's
Thank
cool.
you.
Okay, so let's thank the speaker.
Okay.